Hello everyone, I hope you've been doing well. I'm here to record some brief tutorials for your last two lab assignments, both of which are extra credit, so entirely optional. It's also entirely up to you if you only want to do one, like which one you'd like to do between 6 and 7. There's no requirement that you must do 6 if you're only doing one. So that's entirely up to you, or if you want to do both of them, that's also up to you. Per usual with these SPSS lab assignments, they are worth up to 20 points. So when you look down here, it'll say 0, but that's just because the assignment is not mandatory. But you'll be able to see, as reflected in the different components of the assignment, they are worth up to 20 points. And that goes for each assignment. So if you only complete one, you can get up to 20 extra credit points. If you complete both, you can get up to 40. So that's a really great opportunity. Some students have asked if these points will only apply to points lost on other SPSS lab assignments, and the answer is no. So if you've done really well on these other SPSS assignments, you don't have to worry about any extra credit points going to waste. This is just extra credit points going to your overall grade in general, which is great. If you're going to complete one or both of these assignments, then you just need to submit them by December 6th, which is also reflected down here. So this is a Saturday, so per usual with lab assignments, these assignments, they're due Saturday just before midnight, and not this coming Saturday, of course, but the following. So I provided your data set here for lab assignment 6. And for this assignment, I honestly don't have a ton of stuff to show you just because on par with recent assignments, some of this really relies on you interpreting the output and writing up the results, as well as, a graph, which both of these graphs, which are options for what you can complete. Again, a box plot or an error bar chart. You can choose which one, but we've done at least one of those in other individual assignments. But I'll show you where to go for this in case you've forgotten. But just in general, I really have to show you how to do an ANOVA in SPSS, as well as post hoc tests in case you need to run post hoc tests, or what we call kind of follow-up comparisons. And I'll explain more on that in a bit, but this is really the chunk of what I need to show you in order to do this assignment. And then once I'm done with, this assignment, I'll pause and come back for lab assignment 7. So what are we looking at for this assignment? What is going on with the data? And the data for this lab came from an experiment used to test whether different doses of vitamin C affect the number of days people experienced cold symptoms from one year to the next. So in this experiment, days of cold symptoms were documented across 2 years. The first year before they received the, experimental intervention, you could say, and it could be one of 3 options: either the placebo, where the pills didn't contain any active ingredients, low dose vitamin C, and high dose. You don't need to know the specific doses for the purpose of this assignment or your interpretation. Just understand that there's 3 different groups. One placebo. Could also be, some people, conflate placebo and control group. Placebo is still administering a treatment, albeit that treatment has no active ingredients, but you are administering a treatment, at least as far as the participant is concerned. So maybe not considered a true control, but a condition with no active vitamin C. And then a low dose versus a high dose. And sometimes designs like this are used to test kind of the sensitivity of a dose, like a treatment. So is it that as you increase dose, the outcome is better or different? Or is it as long as someone is, taking vitamin C, they experience less days with cold symptoms? Sorry, getting tongue-tied. I'm getting tongue-tied as I'm saying I'm getting tongue-tied. But anyways, so this could be considered like to test, again, the sensitivity of a given treatment, if higher doses or differences in doses are meaningful, or if just receiving the treatment helps. And then it doesn't really matter what your dose is, which is, not usually the case with medication or interventions like this. But it could be the case, especially with different people. You don't know. That's why we're testing it. We're here to find out. But a big thing to consider here is, we've done a similar, statistical test to this in terms of testing whether, the means of two groups, the mean for a dependent variable of two treatment groups is statistically different from one another. And that was our t-test. However, with a t-test, you can only compare two groups against one another. So in cases where you have more than two treatment conditions, whether it's to test a control and then a low dose and high dose, or a variety of different conditions to see its outcome on a certain dependent variable, you cannot use a t-test whenever you have more than two groups. And the straightforward answer is that is what the t-test is capable of. It can compare two means against one another to see if they are statistically different, or just, any differences could be due to chance. So when you have more than two groups, I guess I could use, textbook horrible practice of the kind of standout example of what not to do, which is if you know how to do a t-test, some students going from a t-test to an ANOVA can be intimidating. So maybe, not saying anyone has thought this, but maybe the most straightforward logic would be, well, if I know how to do a t-test and that's not as scary to me, in ANOVA you get, a little bit more complicated with the output. So I'm comfortable with the t-test. Why don't I just run multiple t-tests to test differences between all of these groups? So I could run a t-test of the placebo versus the low dose, the placebo versus the high dose, and then the low dose versus the high dose. So that's 3 different t-tests that could technically test what we're trying to do with this ANOVA, right? We want to see, are these groups different from one another? And you want to compare each group against each other. But the answer is, if it's not obvious, that is a horrible idea for multiple reasons. On the one hand, why run 3 separate t-tests when there is one test that can do all of that at once, for efficiency's sake, for reporting statistics? Like, why would you report 3 separate tests when there is one test that can, give you your answer? So that's one answer. That's maybe the most straightforward or, surface level obvious. But the underlying reason as to why we don't do that is because when you run a statistical test, and that applies to t-test or ANOVA, but any given statistical test has a probability of detecting a false positive, or to maybe scare some of you with the terminology, a type 1 error. But keeping it simple, a false positive. So every statistical test, one way or another, has a chance of detecting a false positive, just because that is always a possibility. It is possible that just how it's possible to detect a false negative, where you don't detect a difference in the data when one really exists in the population. So for some reason in your data, you didn't detect this difference, but a difference really exists out there. So there's always a chance for both when conducting a statistical test. And you want to keep that probability of that happening as low as possible, even though it's always possible. And the simplest way that I think I can explain this without pulling up PowerPoint and doing a mini lesson the easiest way I can explain this is that with each additional test you do, that chance of a false positive is just compounded. So if you were to do 3 separate t-tests just to test the difference between these 3 groups, you're just compounding the chance to detect a false positive, one test on top of another on top of another. Whereas a one-way ANOVA can test the difference between these 3 groups all at once, keeping the same probability of detecting a false positive as if you were doing one t-test at a time, say. Or just you're keeping it as minimal as possible. Again, you can't ever eradicate those possibilities entirely. There is always probabilities for false positives, false negatives. There is no way to completely ensure or prevent against that, but what you want to do is minimize that probability. So you do not want to be introducing extra error or extra probability for type 1 error, that false positive error, or that false positive probability, by stacking those tests on top of one another when there is one test that can do it, like it's a person, when there is one test that can do it all while keeping that probability for type 1 error very low. So you don't want to, kind of compound or exacerbate those probabilities of false positives on top of one another, which is exactly what would happen if you do 3 t-tests to compare these groups rather than just one one-way ANOVA. Hopefully that makes sense. So brief little, hopefully a refresh or just preview into why the ANOVA is necessary. And again, it doesn't have to be 3 groups, it can be more, but just anytime you have more than 2 groups, you cannot use a t-test. Both for feasibility, like SPSS literally won't let you use a variable with more than 2 groups. So you can think of it that way, but also for the sake of data integrity. So one way to think about it is the ANOVA in this case. Not only is it just the correct practice, but it is giving you the most conservative probability that a type 1 error or a false positive could exist. Again, there's no way to completely eradicate this, but you want to keep it minimal. And when, reporting these things and publishing, this is something that, peer reviewers are looking for. Are you going with the most conservative approach? And if you're not, for some, there's are, we'll get more into this with the follow-up test. There are some cases where the more conservative approach, or basically you're reducing your power to maybe detect a difference in order to reduce the probability that you commit a false positive or a type 1 error. And essentially the logic there is you would rather report null results or no differences than report a false positive in terms of research integrity. You would always rather report no statistical differences, null results, boring results, as some might call them, but you would rather do that than report a difference that doesn't really exist. And yeah, these are just things on how to reduce that error, reduce that likelihood of that happening. So you want to be, whenever you're reporting results, and especially trying to generalize findings, so say you're trying to report, I found something really interesting, and I want to say, this has implications for, healthcare or, people's health in general. You want to be as conservative as possible when you're making a claim like that. So to do that, we have certain statistical tests you should use in certain instances, and also certain post hoc tests. So we'll get to the follow-up comparisons or the post hoc tests. Again, those words are kind of used interchangeably, but you should know what post hoc test means. But again, it just means follow-up comparisons. It's just a different way to say it. But so we have these different treatment groups. What are we looking at? So as I mentioned, we're looking at the change in days people experience cold symptoms So year one, they, collected days, the amount of days people experienced cold symptoms, then administered one of 3 treatments, randomly assigning participants to one of these groups. And then across year 2, while having the treatment or the intervention, collecting the same information. How many days did they experience cold symptoms across that year? So year 1 can be thought of as like a baseline of how many cold symptoms they how many days they experience cold symptoms in a given year without the treatment. And then year 2, how many days they experience cold symptoms with the treatment. So the actual outcome variable we're using is the change in number of days with cold symptoms between the 2 years. So taking year 2, number of days experiencing cold symptoms in year 2, and from that subtracting number of days experiencing cold symptoms from year 1. And lower scores here are going to indicate fewer days of symptoms in the second year. And lower scores here also means like negative scores. So more negative scores, again, because year 2 is the year that they were taking the intervention or the treatment, either the placebo, low dose, or high dose. So if this number is lower than the number of days they experience cold symptoms in year 1, which would be the case if the intervention is working, quote unquote, or improving cold symptoms. So in this case, the value would be negative. So lower scores, including more negative values, so lower, more negative values indicate fewer days of symptoms in the second year. Okay. So we have some other variables in here just because that data was collected, but we're not using it for the purpose of this lab. And the goal of this assignment is for you to kind of make a determination whether from this data there is evidence that the mean change in cold symptoms differs across the 3 treatment groups. And again, there's no directionality here. So it could be 1 and 3 differ, 1 and 2 differ, 2 and 3 differ, like whatever it may be. Does a difference exist across the 3 groups? So first part of the assignment, conduct the ANOVA. So all you need to do, open up your data set. As I mentioned, you have ID, gender, age, group, which is our treatment condition, and diff. And I'm realizing that this doesn't have the values added, so I'm gonna get this added and then upload the new data set so that you have these labels in there. 1 second. Okay, so I have updated the file download in the assignment details. So now you have these values here, so this is already taken care of for you. So your group, again, looking at this, 1 represents the placebo group, 2, low dose, 3, high dose. All right, so we can go here, and also here's our data. So conducting a one-way ANOVA, you're going to go to Analyze, Compare Means, which is similar for our t-tests. I can also show you there are multiple ways to get to a one-way ANOVA, but this tends to be the most user-friendly because it's literally called one-way ANOVA. And the way the Analyze is broken up here, Compare Means is exactly what we know an ANOVA to be. We're comparing the means between these different groups to see what is happening. Are they different from one another? Are they the same statistically? So compare means is very intuitive, and then it's called one-way ANOVA. So once you get to here, you're in great shape. Another way, however, just so you know that this exists, similar to our graphs and how there's like chart builder and legacy dialogues, there are sometimes different paths to similar answers. So general linear model, univariate, it sounds complicated, but the uni standing for that one way or one independent variable. So multivariate in this case would mean that there are multiple independent variables or groups that you're testing. And this brings in things like interaction effects. And an example of this, you can do two different like treatment groups, like two, and I don't mean like groups like low dose versus high dose, like two different variables that have their own conditions. So for example, some people do, maybe if you're testing like music, for example, music's effect on exam performance or studying, whatever it may be. Say you want to test both type of music and like, I'm trying to think, maybe volume. I'm trying to think of a categorical variable because they would both need to be like grouping variables, nothing like continuous. So maybe you want to test different volume levels. So like classical music versus hip hop, pop. Say you have, more than two groups in terms of types of music, but then say you have different volume levels. Maybe you have a predetermined, and if this was in a lab, like a lab study, you could easily do this where one like set of headphones or whatever it may be is set to a low volume, and then you would need to define like what that low volume consists of, like what did you categorize as your low volume group versus moderate versus like high volume. It just couldn't be like continuous volume, if that makes sense, because one, that would be kind of hard to study, but you can't do a ANOVA with a continuous predictor. That's when we get to regression, which correlation or regression, and it's a different type of test that you have to use with continuous predictor variables. So anytime you have grouping variables, so different treatment groups, or if even different categorical variables. So sometimes people use multivariate or a two-way, three-way ANOVA, which just means basically when we say one way, this is really just the one is signifying how many predictor variables or grouping variables, categorical variables, are predicting your outcome. So not that there's one treatment group, but that there's one variable that you're manipulating that has more than two treatment groups that you're trying to compare and see if they have different means of whatever outcome variable you're testing. So one way, one independent variable, two way, two categorical variables, and that's when you get into this multivariate. And then it can go beyond two way, which gets very complicated, obviously. But the point I was going to make is that you don't need different treatment intervention variables to have a multivariate. So maybe you only have one intervention. So say here we have the vitamin C treatment as our group that we are randomly assigning people to. We are experimentally manipulating, but maybe we want to look at if gender interacts with their treatment group to lead to changes in the outcome variable. So essentially, maybe different treatments have different effects depending on gender. Hopefully that makes sense. As in, maybe women are more or less sensitive to vitamin C treatments than men, or vice versa. That would be I'm not saying that's true. I'm just saying that's an example of what question you're trying to test if you were bringing in gender. So again, it's another categorical variable. And in this case, gender, like in this data set, only has two options. But as long as you have one group, like if you were just looking at gender and experience, like days experience cold symptoms, then you would just do a t-test because there's only two groups. But because you're using an intervention here that has up to three groups, you need an ANOVA. And then anytime you add an additional like independent variable to your model to try and predict this outcome variable, it would still be an ANOVA. Like you can't take away like the necessity for an ANOVA just because you have an additional independent variable that only has two groups in this case. Hopefully that makes sense. But again, if we were just looking at gender and the outcome variable in this case, where we only have 2 groups in this data set, then we could use a t-test. But again, the incorporation of this additional variable, one, if you're testing multiple independent variables, you absolutely need an ANOVA. A t-test, again, is not capable. Not only is a t-test only capable of using 2 groups, but it's only using one predictor at a time. And ANOVA has the capability to introduce additional variables. So in terms of predictor variables, like how is gender and treatment group predicting differences in this outcome variable of difference in days of cold symptoms experienced across 2 years. ANOVA, again, I kind of gave the spiel of why you need an ANOVA for more than 2 groups, but again, more than 2 predictors, you also will need an ANOVA as long as those predictor variables are categorical. Okay, moving on. I've showed you how to do an ANOVA. So once you get that output, or I've showed you where to find it. Here, let me give you a little bit more information. So I've showed you how to find it. Univariate, again, is an ANOVA, but the box looks a little bit different because it, brings in the possibility to look at some other things like covariates and stuff like that, but it's still an ANOVA. But for the sake of this assignment, just rely on going to compare means and then one-way ANOVA. And here it's very straightforward. We're only dealing with 2 variables, so you just need to make sure you get the group variable into the factor box and the diff variable in the dependent list. And in this case, you can introduce multiple dependent variables in your model. So if you were interested in how we don't have another dependent variable, like intervention group can't predict something like age, so it's not relevant here. But say we had number of doctor visits across the 2 years, maybe, I don't know. So you can introduce multiple dependent variables in the model, but we just don't have any that we're interested in, none included in this data set that would be applicable or interpretable. Then you have some options over here. So preview, there is an option for post hoc test. So contrast, don't worry about this. I'm not even going to touch on it because it's just not important for this assignment, and I'm already explaining slightly advanced topics in terms of explaining the multivariate models to you guys, or 2-way, 3-way ANOVAs. But I just wanted you to understand the difference and different paths to get to the same thing, or why an ANOVA is appropriate in these different cases. So contrast, don't even worry about, nothing to do there. Post hoc, I'm going to come back to, but you are going to need that. Options. For your write-up, you need descriptive statistics, so I always recommend getting that. Anyways, because you always report that when you're reporting the results of a statistical test, you always need the descriptives as well. And then for this assignment, you also need the homogeneity of variance test, as we've called before the Levine's test. Similar concepts here, but these are the 2 you need checked. So options, be sure these 2 are checked. And then bootstrap, also you don't have to worry about. So just, I'm showing you that that's there, but I'm showing you don't have to do absolutely anything with it, which is great. So at this point, you would hit OK and get your output table, and then go to your assignment, interpret your output, and decide, okay, what do I need to do from here? Do I need post hoc tests? And the reason I say we'll come back to the post hoc tests is because the output of your ANOVA here determines which post hoc test you're going to need in this case. So we've talked about this before, but again, the Levine's test, in terms of assuming normality, you want it to be non-significant, and it has its own p-value associated with the Levine's test, separate from the p-value testing the overall ANOVA, or difference between groups. So the Levene's test is really for testing normality, and the non-significant result means that equal variances or normality can be assumed and moved forward with, whereas if equal variances cannot be assumed, that means our test was significant, meaning it found significant differences in these variances to the point where we cannot assume normality. So I'll show you an example of where to look for the Levene's test p-value, and then where to look for the p-value of the overall statistical test, which tells us, are there significant differences between these groups? So the reason for these post hoc tests, so again, once you have your output from, the first part, you decide which one to go with. So again, the Levene's test tells you, can equal variances be assumed or not? And then that tells you which follow-up comparison test you can run, because there are a lot of different ones. And we're not going to go through all of them, but I'm going to briefly touch on why they're different. And but overall, why do we need a post hoc test when we've run the ANOVA? And the answer is that the ANOVA will give us, the answer in terms of, are these groups significantly different from one another in some way? So is there a significant difference across treatment conditions? But then what it doesn't tell us, we'll get the descriptives from our output, but it doesn't tell us precisely which group is statistically different from another. Is it all of them? Is it only some of them? Again, and we can look at the descriptives and say, okay, maybe one's scoring higher or lower, but that is still not telling us which groups specifically are statistically different from one another. Because it's possible to have all of these in the model and have a significant model, but only, some of the comparisons are significant and others aren't. So maybe placebo is significantly different from low dose. Placebo could be significantly different also from high dose, but maybe low dose and high dose are not significantly different from one another in terms of the dependent variable of number of days, change in number of days with cold symptoms across the 2 years. So it is possible for us to get a significant result in our overall statistical test, the ANOVA, but we still need to, one word that is used commonly is probe or understand, dig deeper to understand which groups specifically are scoring statistically different from one another. So we know that some statistical differences exist, and we can look at the descriptives or the means to say, oh, one is scoring higher or lower. But until we do the post hoc test, we cannot be confident which ones are specifically different from. So again, is the placebo statistically different from low? Is the placebo statistically different from the high dose? Are the low and high dose statistically different from one another? So yeah, are we seeing statistical differences when comparing every single group or only some of them? Because any number of variations of those could be true, and we need to know in order to report our results with greater accuracy. We need to know specifically which groups are actually different from one another. So you have to do your ANOVA first. That tells you which follow-up test you should conduct. And then your post hoc test provides the necessary information to test the different means against each one. So again, the overall ANOVA is telling you that a statistical difference exists among your different groups that you're testing. And then the post hoc test is basically a follow-up comparison to tell you, okay, which groups it's testing each group against the other one, to see, okay, is this mean specifically different statistically from another? Are all of the comparisons statistically significant, or only some of them? And in most cases, when dealing with real data, you're dealing with like certain comparisons are significant and driving the significant effect of the overall model. And then that also gives us important like interpretation of if, say, these two groups are not statistically different from one another, maybe the difference in doses is not enough to, lead to maybe there's like a ceiling effect, like once you have a certain dose, that's as much improvement as you're going to see. So higher dose doesn't necessarily help. And that's informative because maybe a higher dose is more likely to lead to like other like negative side effects. So if you don't need a higher dose and you see those benefits just in terms of decreasing number of days with cold symptoms, if you see those benefits with the low dose and there's not a significant improvement between the low dose and the high dose, and it also might depend on the person, but and a variety of other factors, but that's the type of information we're getting from those like follow-up comparisons, and those are the things we want to be able to interpret. And then if they're all different from one another, we want to be able to like report that and say, low dose, had significantly better outcomes in terms of number of days with cold symptoms than placebo, and then high dose exhibited that as well, and then high dose exhibited better outcomes than low dose. Like we want to be able to communicate that and spread those findings in either case. So if there are, if not all comparisons are significant, we want to be able to express that. There's some important nuance there. If they're all significant, we want to be able to communicate that. Okay, so now I will show you what those output tables look like and how to read them without showing you my output. So I need to show you, now that you've done your one-way ANOVA and you've determined which follow-up tests you should run, you can come back to analyze, compare means, one-way ANOVA, and these variables should still be here, or you can move them over again if it happened to reset. But so now what you need to do is go to this post hoc box. And you can keep everything else the same, but what you want to do is check off the tests that you need. So it has it broken up really nicely in terms of tests you run if equal variances are assumed, and that doesn't mean you run every single one. You pick one, and there's different logic, but in terms of why you pick one of these over the other, as well as here. But it's really nice that they have it broken up in terms of these are the tests for when equal variances can be assumed, and these are the tests for when it cannot be assumed. And obviously has your significance level here, which we are keeping the same. So if equal variances cannot be assumed, or your Levene's test p-value was significant, meaning it was lower than 0.05, that means you would come over here and check Dunnett's C. If equal variances can be assumed, meaning the p-value for your Levene's test was not significant, so it exceeded 0.05, then you can go with Tukey, which I always think that name is so funny. And there's some different tests here, and then obviously you have a different version of Tukey's, Tukey's B, which I'm honestly not familiar with. So I will tell you Tukey, and it might be labeled differently because as we've, encountered in previous lab assignments, different versions of SPSS have slightly different variations in how things are maybe labeled or how they appear. But in general, I'm telling you, it's either going to say Tukey, like how it says right here, or it could match more closely and say Tukey's HSD. And what this means, I'm not going to get too far into this because it could go on forever, but it just means highest significant difference. And funny enough, Tukey also has another test, but it's labeled differently here under LSD, which just means least significant difference. So there are variations of the same test with different levels of conservativeness when trying to detect a difference. And in this case, we want a more conservative test, again, to reduce our likelihood of committing a type 1 error, of getting a false positive. So as I mentioned, when we should run an ANOVA. When we do these follow-up comparisons on a very simple level, it's essentially running those t-tests that I mentioned in the background, which is very confusing in terms of, I said, don't do that. But in this case, we are choosing basically the level of conservativeness in conducting those follow-up comparisons. So in this case, we are being very intentional about saying we're picking a more conservative test in order to run these follow-up comparisons, so we decrease our likelihood of committing a type 1 error or detecting a false positive. So like with everything super complicated, it's like I tell you a rule and then I give you an exception to that rule. So it's like, don't do the t-test to test, don't do multiple t-tests to test these different comparisons. But essentially, this post hoc or multiple comparisons, follow-up comparisons, whatever you want to call it, is a way to do controlled kind of chaos or control the level of error that you're introducing. And essentially, Tukey's HSD is known to be one of the more conservative or basically reduce that chance of type 1 error. Same thing with Bonferroni. I'm most familiar with these two. I'm not saying these others are not, great or important. I'm just letting you know that I think the ones that you'll tend to encounter the most if you, encounter more stats in the future is Tukey HSD, Tukey LSD, Bonferroni, and I also see Chef quite a bit in terms of when equal variances are assumed, at least. Okay, that's a lot of information, but essentially Tukey HSD, or highest significant difference, is the more conservative test, while LSD, least significant difference, is the more, I guess you could call, it's not correcting as much for that possibility for type 1 error. So essentially the type 1 error probability or probability of detecting a false positive is higher here. And essentially the reason this exists, so the question could be, why does this even exist if it's, less conservative, it's, has a higher tendency for type 1 error? Why is that an option? And, sometimes it really just depends on your study design. Sometimes you are extremely underpowered, or maybe you have a very, when I say underpowered, I mean you have less power to detect the differences that could exist, even if they do exist. You just don't have a big enough sample, or maybe you have a lot of noise in your data. Something happened, who knows? But in some cases, you have very much reduced power to detect a difference, even if it exists. So maybe you would go with this least significant difference test because you're like, well, I'm already underpowered. So then to choose a more conservative test, there is literally no way that I'm going to be able to detect an effect. So again, it's a matter of, there's differences in opinion in terms of across statistics and which test to use, but also context matters in terms of the study you're running, the variables, how much power you have. If you're very underpowered, again, that's when you might consider a more these least significant difference tests, because if a difference exists, it will be able to detect it, whereas the more conservative tests, might not be able to detect it. Sometimes people run both. I don't recommend that, because you don't want to just run everything and then just choose the thing that goes with your, say you run all of them and you're like, oh my God, the least significant difference test is detecting effects, so I'm going to go with that one. That's, a version of what we call p-hacking, or just doing all the things, running all the analyses until you find something that sticks and then reporting that. That is not recommended. But again, sometimes there might be cases where you would run both to see if I pick a less conservative test, is a statistical difference emerging? Or if I run both, like, there's nothing there. Sometimes people do that to see, is something approaching marginal significance? So maybe if I had a bigger sample, greater power to detect a difference, would I be able to? There are different contexts where that matters. So that's a lot of information. But essentially what you need to know is to go with this Tukey test or Tukey HSD, highest significant difference, as this is the more conservative test we want to go with. Again, that's if equal variances are assumed. If not assumed, you would want to come down here to Dunnett C. So depending on what you go with, you're going to hit continue and then run your one-way ANOVA again. And then that will give you the multiple comparisons or post hoc test output that you need to complete the assignment. I have another one of my makeshift boxes to hide the output, but essentially I just want to show you the different tables that you're going to be the different tables you're going to have in your output when you run how I've showed you to run the ANOVA, and then specific things that you need to be looking for, or like the specific spots you need to be looking for certain values. So the first thing you're going to get, which you absolutely do need, especially when you checked off the descriptive option. So yeah, if you don't check that off, that won't be here, which you need it for the write-up. But this is just giving you the means and standard deviations of the different groups, placebo, low dose, and high dose, on that diff variable, so our outcome variable. So this is giving you all the descriptives you need, which, as you know, a reminder, you do report in your write-up. So you're going to need the means and standard deviations for each group. And another thing people typically report also is like the balance among the groups, to make sure you got like a somewhat like even split, so you don't have like 40 people in the placebo group and then you're trying to test them against one another. That wouldn't be very informative. And then the next table after the descriptives is the test of homogeneity of variances, which again is another way to say the Levine statistic, or the the test to see if equal variances can be assumed or not. Then when looking at this table, there's some different rows here for based on mean, median, and some different adjusted measures. And that's just, if you have reason to believe that there's like some major outliers in your data, maybe you'd be more interested in the like median result versus the mean. But if there are no issues with extreme outliers or anything like that, you'll see that the results on the different like rows will be very similar. In other words, there's like no advantage to interpreting like one over the other. So that's usually the case if you have, normal distribution, normality can be assumed, all of those things. So when deciding which post hoc test to run, or if equal variances can be assumed or not, this is the p-value or sig value, significance value, that you want to pay attention to. So it's in the test of homogeneity of variances. It's next to the Levine statistic. So you're going to be paying attention to whether or not this p-value is significant or non-significant. And if it's non-significant, if it exceeds 0.05, that's when you go with the equal variances can be assumed. And if it is significant, it is below 0.05, that's when equal variances cannot be assumed. Okay, so the next table you'll come across is the actual ANOVA table. So for this one, this is the result of your overall statistical test. So when you initially run your ANOVA without checking for post hoc comparisons, this is the table you'll get, in addition to the Levine statistic table and the descriptive table. But this is the main, it will end here in your output. after you initially run that ANOVA. And then again, you interpret that Levine statistic, and then you go back and run it for whichever post hoc test you think is appropriate. So for this one, what is important here is one, the p-value for the ANOVA table. This is the one where if it is below 0.05, this is telling us that our treatment variable, our independent variable, the different groups are like, there is a significant difference among the groups, whether that's between whatever groups or comparisons are significant. It's just telling you that the independent variable is significantly predicting differences in the outcome variable across the groups. So between groups, not specifying which groups, but it's telling you that there are some significant differences between groups of this independent variable, or our vitamin C dosage, essentially. So what you're going to report, definitely refer to one, just I always recommend like APA format of reporting these results, but in the little sample text I give, without like giving an example of exactly how to write it up, I do tell you what values, what's statistics here that you need to report. And as I mentioned before, the overall test statistic for an ANOVA is the F value. For a t-test, it's the t value. So you're going to need the F value along with degrees of freedom. I always say pay attention to this first row. So for the purpose of the assignment, just pay attention to the numbers in the between groups row. So don't worry about the within groups row. There's not always data in every single column for the within groups row. That's a hint as to that's not what you're interpreting. But another hint as to which row you should pay attention to is that we are comparing the difference between groups. So between groups is what we're interested in. So we want to see, is this group different than this group, not the difference within a single group, essentially. So that's as far as I'll get into that for now, because it's complicated, but of course. But you're going to pay attention to the values in this between groups row. So there should be values in each column for this top between groups row. And you're going to need the F statistic, degrees of freedom, and the p-value. So if the p-value or sig value in this ANOVA table is below 0.05, that is telling you there is a significant effect of treatment group on the outcome variable. Again, that's not telling you exactly which groups are different from one another statistically, but it's telling you there is a significant effect here. All right, so moving on to our last table of interest that you need in your output. So I ran both the Tukey's HSD and the Dunnett-C test. Again, you're going to run one or the other depending on your Levine's test, but they are presented in the exact same way, as you can see from like them being included in the same table and having like repeated format. So really it's just basically in the background conducting different tests in order to, based on whether or not equal variances can be assumed or not. So that's really what you need to take away from this. But essentially what this table then tells you is, the way it's set up can be a little confusing at first, but essentially it is showing you, each group and then comparing against the other group. So this is taking the placebo group, and then this row up here next to low dose is comparing placebo and low dose. And then in this next row, placebo and high dose. And then it goes on, so on and so forth. So you won't have as many, rows here because you'll only have either Tukey HSD or Dunnett-C. So this is a bit, it's extra repetitive because it's testing the same things, just using different background tests or different methods for testing for comparisons. And then it's going to take the low dose compared to placebo and high dose. And this is ensuring that you're getting every single comparison, although there will be some, you'll see the same information kind of reported because it's like placebo and low dose and then low dose and placebo. So like these values should mirror one another. And it's also a good way to check to make sure you're interpreting things correctly. But essentially, the important part here is you're going to look at these significant values. So each of these rows, like again, depending on which follow-up comparison you're using, is going to have a p-value. And it's telling you, is placebo versus low dose significantly different? Is placebo versus high dose? Is low dose versus high dose? Like all of those comparisons, that's what it's telling you here. If they are significantly different. So the important thing to report here is if there are significant differences between group, you want to be sure you report those, both their descriptives. So that's when you'll like plug in the mean and standard deviation for the placebo group, the mean and standard deviation from the low dose group, and then say, were they significantly different from one another? And then after you report the descriptives for one of the groups, you don't have to like keep reporting them. So if you already reported placebo, but then you're talking about placebo versus high dose, you don't have to report the descriptives or means and standard deviations again. Like as long as those are reported once in the write-up, that's totally fine. But you do want to report the p-value for that comparison so that your audience knows whether or not it reached statistical significance. And then interpretation-wise, you can also just, if a comparison is significant, then you can go to those descriptives and say, okay, the placebo scored higher, lower, like whatever. But then you can go to the descriptives to interpret that statistical difference. Again, you can always point to, oh, this, their mean is higher than another, but you want to note whether that difference is significant or not. These are where you get your comparisons, and the important values that you're getting from this table are the p-values. Of course, you can look at the mean difference. This is just literally going to tell you the mean difference between the placebo and low dose scores. So it's a little bit harder to interpret. So what I recommend doing is using the p-values to determine whether a comparison reached statistical significance, and then go back to the descriptives. Okay, the placebo scored lower or higher than low dose, so on, so on. And that's what I recommend doing. Okay, there's another table down here, and for the purpose of the assignment, you don't need to know anything about it. As I mentioned, as we saw in, the post hoc box here, the box I checked off when I ran this test just said Tukey, and then when it printed here, it says Tukey HSD. So just keep in mind if you see something similar to this, as long as it says just Tukey and not the -B, it's correct. And then in some cases, LSD might also have the Tukey in front of it, because they're both, again, it's a version of the same test with different levels of type 1 error, probability for type 1 error. So Tukey or Tukey HSD is the more conservative test, meaning it can only detect really strong, statistically different results, whereas LSD is going to be a little bit more lenient, forgiving, less conservative in detecting those differences, but that means there's a higher probability for type 1 error. So as long as it says Tukey or HSD and it doesn't have this -B or LSD, you have picked the correct test. And again, it might reflect in your output like this. And then again, Dunnett C is a little bit more straightforward because it's labeled the same way. That was, where's my tab? There it is. Okay, so in terms of your lab assignment, we've gone over how to do an ANOVA, how to determine which post hoc test to run, as well as how to look at the output to report the results of the post hoc tests. For the graph, I'll just briefly point you to where you need to go. Again, the assignment explains you either need a box plot of your outcome variable by group, so just seeing the spread of the dependent variable or difference in days experiencing cold symptoms from year 1 to year 2. So you need that broken up by group, or an error bar chart showing mean values with error bars. And then we've done this before, but set error bars to represent plus or minus 2 standard deviations. So going back to our data set, for the graphs, you just need to, as a reminder, you can go to Chart Builder, or Legacy Dialogues has both the box plot and error bar. So I feel like this is typically what we do, but Chart Builder also has an option for box plot. So what you need to do here, if you're doing a box plot, you need the simple summaries for groups of cases. You need your group in the category axis, and then diff in variable. And then if you were doing the error bar, oh wait, did I just do that? Or do they look the same? I can't remember. Oh yeah, they just look the same when you're building them. So yeah, simple enough. So if you're doing an error bar, you'll select the error bar group. Oh yeah, I forgot it has the extra bars represent. So yeah, it looks very similar either way, similar process. Diff goes into your variable, and then group goes into your category, and then you would want these to be bars represent standard deviation 2. So the main thing I wanted to note with the write-up is, you have all the information you need in terms of, I've told you where to look, but the one thing that is not necessarily intuitive, the F value is reported here. So the test statistic, that F value that I pointed you guys to. The information in these parentheses is sometimes confusing, but essentially what this refers to is the degrees of freedom. And the reason why it's 2 is you report the degrees of freedom value in that top row that I showed you guys, the between groups row. And then after the comma, you report the degrees of freedom value in the very bottom row of the ANOVA table, which is the total degrees of freedom. So essentially you're reporting degrees of freedom for the between group comparison and the degrees of freedom for the overall model. This is probably the least intuitive in terms of what you're reporting, are these degrees of freedom values. So the F, or test statistic, goes after the equal sign, and then your p-value, which we're obviously used to, but in the parentheses after the F, so it's not the F value that goes here. In terms of within the parentheses, this is not the F value or test statistic. These are the degrees of freedom. And this first value is coming from the first row, the between groups row. This is the degrees of freedom value, DF value for between groups. And then this is the degrees of freedom value in the total row, or the bottom row of the ANOVA table. I think that was the only thing I wanted to know in terms of being careful of what values you plug in. But other than that, you have absolutely everything you need here in terms of how it will be graded. So this is what you should include. Okay, when I come back, I will be walking through lab assignment 7.